Hey everybody, happy Thursday. Thanks so much for joining us. Our SageMaker webinar today is going to cover DeepAR forecasting, and I know that Chris Skrinak is fired up to get started. I am Sue Ewig, and I'm the AWS Global Partner Marketing Manager for AI and Machine Learning. You guys in the audience, everybody attending the webinar belongs to one of the 12 consulting partners who have achieved the AWS machine learning competency. So thank you all for being here. This is a private webinar for you guys, and we want to make sure that you can ask any and all questions that you have. So feel free to pop those into the, there's a right nav that's part of the GoToWebinar platform, and you should see a questions section. If you don't see questions, feel free to pop those in chat. Chris Burns, Chris with the C Burns, is going to be kind of monitoring that section and trying to get those questions answered, while Chris with a K, Skrinak, presents for you today. So Chris Skrinak is a partner solution architect for AWS. He leads the machine learning segment globally, and Chris Burns is also a PSA for AWS who's focused on AI and machine learning. So let's jump into this really cool topic and let Chris take it away.
Well, hello, everybody. I'm speaking to you from New York City, communication capital of the world. So this series provides our partner network with an in-depth look at the built-in algorithms of SageMaker. And so in that light, I'd like to first talk about how do we choose the algorithms that we're going to build in. Of course, there's a lot of choices, right? The open source community, we have scikit-learn, SciPy, NumPy, you can build stuff. Of course, then there's all the frameworks such as TensorFlow, MXNet, PyTorch, they all come with algorithms. So how do we choose the ones that we're gonna build and present? First of all, they should be popular. They should be algorithms that are in demand, and we see them every day in our workplace, or that we use them here at Amazon. We seek to provide 10 times or better performance on each of these algorithms. So, how do we do that? Because that's a pretty high bar. First of all, we stream whenever possible. So basically, we can use almost anything that uses stochastic gradient descent. We seek to create algorithms that want to see data once and once only. And of course, that means we're going to have to create a shared state, especially when we branch out our training to clusters. So we have built an infrastructure of shared state that enables us to do that. We seek to use GPUs whenever possible. Now, a few of the algorithms don't. K-means, LDA, and XGBoost notably are CPU only. But wherever possible, we seek to use our GPUs, especially the powerful Voltas on the P3 class. We seek to create algorithms that are distributed, that run efficiently in a distributed environment. So this, of course, is a challenge that we overcame when we created this shared state mechanism, right? So in training, we have a set of parameters and statistics that are generated on the fly. And they can be shared. We have some techniques for sharing and generating these on the fly. And you can create many models while you're actually doing the training. We've sort of solved the situation in the past where if you wanted to optimize your model, you had to do hyperparameter optimization and run the same job with different parameters. So this is really a breakthrough of SageMaker, and we use it we seek to use it in all of our built-in models. Abstraction and containerization is another key principle. As you use SageMaker more and more, you're going to discover that we are built on a foundation of containers. There are 4 ways to use SageMaker, through the console, through command line interface, Spark, and of course with the notebooks that we're going to look at today. Last but not least, we seek to efficiently access our data from S3. So when you're doing any kind of training and most work in SageMaker, it's best to do your planning and use the facilities that S3 implements. So those are some key principles. It's something we really don't address too frequently, but we have a product manager here that really just focuses on nothing but what are the appropriate algorithms, and that, of course, is the subject of this series. Last but not least, we strongly favor Record IO protobuf for our file format. There's a couple of reasons for that. When you're storing images, for example, JPEG records, you greatly reduce the size of the data set on disk, and packing data together allows for continuous reading, which improves performance. And Record IO is a simple way to partition and simplify a distributed setting. All right, so time series forecasting. It's very popular. Almost every company can use it. Some of the most popular use cases are improving supply chain efficiencies by doing demand prediction, avoiding outages, allocating computing resources more effectively by predicting web server traffic, even saving lives by forecasting patient visits and staffing hospitals to meet patient needs. Any kind of prediction for urban planning, housing prices, traffic in cities. These are pretty much, many of the common use cases for time series. Within Amazon, we use forecasting to predict product and labor demand in our fulfillment centers, in particular for key dates like Prime Day, Black Friday, Cyber Monday, or making sure that we can elastically scale AWS computing and storage capacity for all of our customers. Now, there are numerous statistical methods that have been developed to forecast time series data, but still the process for developing forecasts tends to be a mix of objective statistics and subjective interpretations. Properly modeling time series data takes a great deal of care. What's the right level, for example, to aggregate the model at? If you're too granular, the signal would get lost in the noise. And if you're too aggregate, important variations are missed. Also, what's the right cyclicity? Daily, weekly, monthly? Are there holiday peaks? How do we weigh this versus the overall trends? Linear regression with appropriate controls for trend, seasonality, and recent behavior remains a common method for forecasting, but we have now entered the era of deep neural networks, and if we have multiple time-related time series, we would want to use SageMaker's DeepAR algorithm, which is specifically designed for forecasting. So just a few definitions. Recurrent neural network, if that's a new term for you, is a type of deep learning neural network where connections between nodes form a directed graph along a sequence. This allows them to exhibit temporal dynamic behavior for a time sequence. So unlike feed-forward neural networks, RNNs can use their internal state to process sequences of inputs. An important type of RNN is an LSTM, which stands for the horrible combination of words, long short-term memory. But an LSTM cell can process data sequentially and keep its state hidden through time. A common LSTM unit is composed of a cell, an input, an output, and a forget gate. The cell remembers values over arbitrary time intervals, and the three gates regulate the flow of information into and out of the cell. When predicting for multiple data points, one step ahead forecasts update the history with the correct known value. These are common and easy to produce and can give us some intuition of whether our model is performing as expected. However, they can also present an unnecessarily optimistic evaluation of the forecast. In horizon models, when forecasting out of sample, each forecast builds off of the forecasted periods that precede it. So errors early on in the test data can compound to create large deviations for observations late in the test data. Although this is more realistic, it can be difficult to create the forecasts, particularly as the model complexity increases. A cold start scenario occurs when we want to generate a forecast for a time series with little or no historical data. This occurs frequently in practice, such as in scenarios where new products are introduced or a new AWS region is launched. Traditional methods here, such as ARIMA, rely solely on the historical data of an individual time series, and as such, they are typically less accurate in the cold start case. Now, probabilistic forecasts are used in DeepAR, and they produce both point forecasts and probabilistic forecasts. So for example, the amount of sneakers sold in a week is between X and Y with Z probability. The later forecasts are particularly well suited for business applications, such as capacity planning, where specific forecast quantities are more important than the most likely outcome. So I want to cover another really important topic, which is what kind of data can you use? All right. So there's a notion, if you're not coming to this from data science, and I know most of you aren't, most are coming from development. You may not know this term of a stationary series. So I'd like to make sure everyone is really clear on what this is. So the true definition is it's a stochastic process where the conditional joint probability distribution, oops, how did I get this thing out of me? Sorry, I can't even read my screen here. Well, you can read it. I won't read it for you, but I don't want to get any of the terms wrong. But basically, you can see on the left, we have essentially a modulation within a fixed range. And on the right, we have an upward trend. The stationary series is characterized by being fixed within that modulated range. Not only can I not see my screen, I can't change the foil. There we go. So that's one definition, or one pretty clear sign of the stationary series. The other, you can see on the left here, we have the plain sine wave, as opposed to one that's varying greatly, and one that varies in cadence or periodicity. I'm just going to clear my screen so I can see my screen when I'm working here. Sorry about that. I'm also sorry that the ad hoc meeting seems to have formed behind me here. Okay, so these are important concepts, and one of the most common misconceptions is that we can just go straight into time series forecasting and start predicting stock prices. I mean, why don't we all just quit our day job and do this, right, at the end of this seminar? Well, here's the S&P 500. I just picked it up this morning, given as a line series with a little bit of data. There's volume data on the bottom. And I would just ask you to say to yourself right now, is this a stationary series? Well, of course it's not. So how do you standardize this? Well, the way we do that typically is through technical analysis. And I'm just going to annotate my screen here just a little bit to point out a few things that I learned working on Wall Street of where you can actually begin this kind of analysis. So you see here we have two indicators that were drawn right into the chart, the prices of the chart themselves. So one, we have an exponential moving average at 13 days, a period of 13, and an EMA of 50. So crossovers in that and the delta between these are an indicator of trend. They're an indicator of the strength of an uptrend, the strength of a downtrend. Down below, we have an even more powerful indicator. It's called MACD, which is moving average convergence divergence, which will combine these exponential moving averages and create a histogram. And the histogram is indicated by the blue bars here. So now we actually have gotten this into a stationary series. So these are really powerful trend indicators. And in fact, you can see where we have a divergence where we cross at the center line on the bottom here, we actually have what looks like a buying opportunity. We have another one here. You could look at that as a reinforcement signal, and so on. And so these are techniques on Wall Street to stationarize our data. Now, I'll just add one more data point here, which is that stock prices on Wall Street move through human behavior. It's not like capturing, the physics of water flow or something. And that's what this chart on the top is really indicating. What this chart on the top is indicating is buying pressure. So as prices, we average out where prices close at the end of the day. And so right here, we would indicate that there was a lot of bullish sentiment and the bulls are getting tired. So maybe you're into a bearish mode here. Now it's the bears have gotten exhausted. So, and once again, this is stationarized data, and you can begin to use it in your analysis with some of the techniques that we're about to cover right now. All right, so let's take a look at some traditional forecasting methods. I'm going to pop over to, first of all, SageMaker. I have an instance running here that is running, first of all, a linear time series. Now, as you may know, SageMaker comes with a number of built-in examples. When you open up a SageMaker Jupyter notebook, there's a tab that says SageMaker Examples, and that's what I'm using here. I'm using a time series forecaster using the built-in algorithm Linear Learner, which Chris Burns covered last week. So let's just walk through this briefly. First of all, we have to create our own bucket to begin to store the data that we're going to download for this particular instance. We have to set up SageMaker and get our IAM role to give us the permissions that we need to run this data. I should cover what our objective here is. So in this particular model, we're going to be downloading I think it's gasoline prices. Where is the data set? Yeah, gasoline prices. And looking at trends and seeing if we can begin to predict them using a linear learner model. Now, you can run this notebook yourself and you can dig in and take your time with this, and that's why I like to choose sort of our built-in notebooks whenever possible. So the first thing we do is download this data set. It's a publicly accessible data set. The first step in any machine learning process is to begin to understand your data, and the best way to begin to understand your data is to visualize it. Now, if your notebook doesn't look exactly the same as mine, don't worry. I've made a few modifications in this notebook to make it read a little bit better for the demo, but essentially this is what we're doing here. We're plotting these gas prices over time, and actually I think this is not prices, but volume of consumption over time. I see thousands of barrels here in the data. So the next step in the process is to break this into a series of segments, and that's what we're doing right here in this. So all we're doing is sort of breaking up the data set so that it's easier to digest in terms of periodicity. Next, we're going to take our data set and divide it into a training, a validation, and a test set. So we have to take special care whenever you're taking a time series data set, when you're doing your training and validation and testing, because unlike many other data sets, the order in which the time series is tested is really important. Simply, you want to use the end of your data set for testing and validation, and that makes sense. Now, I mentioned the importance of converting our data to record IO format. That's what we're doing here. And then we're loading that data up to S3. And then we do that again with our test set and validation. Okay, now we're going to train the model. So here we are getting the container. As I mentioned, SageMaker is built on this foundation of containers, and that's all we're doing here. We have broken up our containers now. They're a lot lighter so that you get them by algorithm name. That may be new to you if you've been working with SageMaker for a while. Then we're going to set our hyperparameters. We only have a few here. First of all, we're going to create a number of separate models so that we can optimize. That's the num models parameter here. So in this case, we're taking the maximum, at least the current maximum, which happens to be 32. So when we run this training job, we're going to use our job queue, which is separate from the notebook, and we're going to run this on a C4X large, and it's going to create 32 separate models and do hyperparameter optimization for us and return to us the best performing model using F1. So and other measures. All right, so this is a pre-baked system. I'm not going to run this right now. It takes a couple minutes. But once that model is ready, and we can see our models when we go back to the console, you just click on models, and I guess it's down here, the linear demo model. We then deploy that model to a production endpoint. So next up, we're going to do some forecasting against our endpoint. There's a couple of ways that we can judge the accuracy of our model. By far the most common and is the root mean square error. And that's what we're going to be using here. So as we go down below here and we begin to plot our results, first of all, we have a model, and oh, I'm sorry, I said we were going to use root mean square error. We're actually using mean absolute percent error. So in the first test, we're using a one step ahead forecast, and we could see the accuracy of this model is relatively good. The next model, our one step ahead model, I'm sorry, I'm getting ahead of myself, is actually a little bit better. And what I'm looking at here, of course, is this indicator right here, which gives us the actual accuracy here as 0.036. Here we've got 0.019. And then finally, our last forecast is giving us a 0.21. So this particular example, and I actually do recommend using the simplest models possible for your particular problem, is showing us that depending on the approach that we're taking to actually do our projections, we can get some very different results. And you may not always need to use something as complex and robust, might be the right word, as a DeepAR. Now, DeepAR does produce really impressive results when you have a lot of data. So that brings up the next point here, which is, when do we use deep neural networks for this kind of situation? Well, it begins with the most important question, which is, what kind of problem are we solving? So basically, when you take a look at very, very big data, so just an obvious example would be looking at the number of items that a company sells based off of the number of sales for those items. And you can imagine Amazon with a catalog like we have a lot of insight into this problem. We could see that magnitudes of time series differ widely, and that the distribution of those magnitudes are strongly skewed. So some time ago, some folks started using a couple of deep learning methods to create an architecture that would do a couple of things, including incorporating a negative binomial likelihood for count data, and also special treatment for the case where magnitudes vary widely. All of this is spelled out in detail in the Amazon white paper on DeepAR. So I gave a big warning up front. I'm sure everybody heard. You can't just throw any data at this kind of problem. First of all, it must be stationary. So if you need to massage your data, if you need to do some feature engineering up front, that may be the biggest part of the job. You're going to want to put that into either a gzipped JSON lines format file, or we do also process Parquet. So what is the contents of this file going to look like before gzipping, of course? First of all, you're going to have a start with a string in the format of year, month, day, hours, minutes, seconds. You're going to have a target. This is going to be integers or floats that represent your time series values. And there's some optional features. So one is to dynamic feature assessment. I'm going to discuss that hyperparameter just a little bit later. And then second, categories. One of the principal reasons to use DeepAR is that you have a very large set of categories that of categorical data that relate to each other. So imagine, if you will, you're selling a lot of different shoes. You may have categories of sneakers versus boots, etc. Well, you can begin to do prediction with these separate categories with very little data, or the data that you have. One other question is, what does the AR stand for in DeepAR? Well, it stands for Auto-Regressive, and Auto-Regressive has more meaning when you compare it to the moving average model. Now, I certainly pointed to a number of moving averages when I showed you that stock screen, and I think you know what that is. But to put it in very, very simple terms, an Auto-Regressive model builds into it the fact that in this particular graph on the top here, let's say you were selling popsicles and it was really cold, it was like 30 degrees, and then all of a sudden you had a really, really warm day. You know, 90, 100 degrees Fahrenheit, of course, if you're not in the US. So popsicle sales just shoot through the roof, right? Then the temperatures kind of go back to normal, and there is this kind of behavior where people buy 50% less than the day before, so it kind of moves out. Now, this can also describe a situation where you run out of inventory on a product or many other kinds of spiky situations. A moving average model simply does not include that kind of regressive approach. So what are the advantages of DeepAR? Well, first of all, there is minimal feature engineering that's required to begin to use DeepAR, because of the fact that the deep neural network models are doing some of that feature engineering for you. If you take a look at these graphs, they showcase sort of the forecasting scenarios using example demand forecasts produced by DeepAR for products sold at Amazon. The first figure shows a cold start scenario. Since the model shares information across items, predictions are reasonable even within limited historical data. The second and third figures show that DeepAR can produce probabilistic forecasts for products with different magnitudes by using appropriate likelihood functions for the setting, which in this particular case happened to be a negative binomial. There's a lot more advantages. We provide support for different types of time series, real numbers, scalars, etc. We provide automatic evaluation of model accuracy. It is engineered to use either GPU or CPU hardware to train the LSTM and the RNN quickly and flexibly. It scales up to data sets comprising more than 100,000 items in time series. And there is support for training data in JSON lines or Parquet format. Also, importantly, we support missing values, categorical and time series features, and generalized frequencies. Here's a quick look at the architecture, and I will not go into too much depth here because certainly the papers do, but I do want to point out that the integration of both the sequence-to-sequence algorithm and the LSTM algorithm. So in training, we see what looks like a typical LSTM rather in encoding, rather, where we're taking our values and encoding them up to samples based on a certain function of likelihood. Then we're using an encoder-decoder model to begin to use our predictions. So we can look ahead, or look backwards actually, with the LSTM architecture in our prediction phase of the model. And that's how we're able to create more accuracy and also predict and also create the windows into which it's best to predict. So once again, I don't kind of want to get into the data science piece of this, and I encourage you, if you are a data scientist, to look at the white paper at archive.org. But I did want to cover the integration of these two deep learning algorithms. So what are the results? Well, once again, if you have chosen the right data set, if it is principally a very large data set with a large number of related time series data, the results are exceptional. First of all, you get all the advantages of running on essentially infinitely scalable hardware at AWS, both in terms of CPU and S3 storage capability. But also, we're beating essentially all the other numbers that are typically predicted for this kind of time series forecasting. So I do want to talk about the hyperparameters just a little bit. First of all, it is obvious that you have to choose some sort of context length That is going to give you the number of time points that the model gets to see before making a prediction. The value of that parameter should be about the same length as the prediction length. And the prediction length is the number of time steps that the model is trained to predict. That's also called the forecast horizon. We want to take a look at the number of cells, the number of layers. The typical ranges from 1 to 4. Now, choosing a likelihood model, I would refer you to the documentation for certain. But the choices here are Gaussian, beta, student tau, and deterministic L1. The default is student tau. So once again, this is a really sort of an important but nuanced aspect of training the model. And I'll refer you to the documentation for more detail there. Number of epochs, of course, that's the number of passes that we go over the training data. We always want to split things into mini batches to speed up the training process. We need to choose a training rate. We also want to choose a bit of dropout for improved regularization. Dropout, if you're not familiar with that, actually will go into the neural network and randomly delete a few nodes, and that actually helps improve regularization and prevent overfitting. Last but not least is early stopping patience. If that parameter is set, training stops when no progress is made within a specified number of epochs. All right, let's take a look at this. We have 2 great notebooks that are built into SageMaker for this purpose. I'm going to switch first to the notebook that covers, I'm trying to increase the size here, there we go, that uses synthetic or toy data. Now, toy data, you know, has benefits and flaws, but it certainly makes understanding the capabilities of DeepAR really, really clear. Mostly because you can get the data that you know time series in this model are best suited for. And you'll see at the end how that kind of pans out. So let's start at the top here. First of all, I ran this a few times and noticed that I had to upgrade NumPy to run it repeatedly. We initialize our data set with matplotlib and pandas. We install a special module here called S3FS. And now we actually start. So we do our SageMaker setup. We set up our execution role for IAM privileges. We set up our S3 paths. Now we're ready to go. Here again, we're calling the image, the container image that has deep forecasting AR. And now we're going to generate our toy data. I'll note here that when we're generating our toy data, we know in the very beginning that our frequency periodicity is going to be hours and our prediction length is going to be 48. So we have this luxury because we're producing the data that we're going to operate on. We can also set our context length, our T0, data length, number of periods, etc. So here we have, I'll just skip down here, and like I said, if your notebook looks a little bit different, I just reformatted things a bit so that it would look better on this webinar. But here we have a plot of our toy data. So next we're going to divide our data into a test and training set. As mentioned here, the test and training set are differentiated in the sense that they can't be chosen just at random here. They do, when you choose your test set, it does have to come at the end of your series. So we're going to use a special characteristic of Panda series. I've mentioned before that we are using JSON strings format, and when you use Panda series, there's a very convenient function that helps write out our training data in exactly the format that we need. Now we're going to run this through an estimator, and this is our wrapper for that estimator. And here are the hyperparameters that we're going to use for training. Notably, let's see here, we have this early stopping patience of 10. That's really the only one that we didn't sort of set up for ourselves in advance. We refer to our input for test and training as data channels. Here they are formatted here. And then I ran the training job for you before we got on this call. Let me just go to the very bottom and indicate here that we had a total billable seconds of 167 on this particular notebook. All right, now we're going to create our production endpoint and start doing predictions. Here we've created a class that's simply going to help us take advantage of that Panda series convenience function to help us create, to format our prediction call. So this is nice cut and paste code that I encourage you to borrow when you're creating your own notebooks. So now we create the actual prediction endpoint. And this code I wrote too, just to make this next section a little bit more readable. All right, so here we are. Here's the results of our tests. Now, you can see in the, what would I call that, a mustard colored line? That's giving us our 80% confidence interval, which is one of the key characteristics of DeepAR, the ability to do probabilistic forecasting. The orange line, if you wanted a hard number, is the hard number. It is the actual predicted number. And what we're displaying here with these 5 different graphs, and you could tell when you look at the left-hand margin, just at the range here, we have 3 to 5, 4 to 8, 4 to 6. So these are clearly different categories of data that have been trained with the data set. The next notebook that we use, this will be a little bit more explicit because we're going to use real data from an electrical power plant forecasting site. But what you can see, if you imagine, for example, the first one is boots, the next is sneakers, the next is maybe a brand new product that we never introduced before, some kind of, you know, slipper or something, that we have pretty accurate models. In fact, you can only see a little bit of target data exceeding our 80% boundaries. It does happen, but you got to be a stickler for detail to see that. So that's a pretty successful model. One other point, I encourage you to run these sample notebooks, dig into them, copy and paste the code. All of this code is in GitHub. You can actually do pull requests on this code. I wish you would. But when you're running it, I commented out this last command here because I wanted to preserve my endpoint for this demo, but always delete your endpoints if you're not going to use those in production because they can be costly. All right, next up, we have real data. And just to be super clear, at the end of this presentation, in just a few moments, I have links to all of the information that I've covered here, including a few open source references on the data science behind predictive forecasting, and also links to these specific notebooks in GitHub. So in this notebook right here, we're going to actually use some real data that's available from UCI. So we do the usual setup. I won't dwell on that. Usual things we need to do, set up our buckets. And here we are with the UCI data set. We're going to download that from the UCI dataset repository. By the way, I have a great collection of public data sets. If anybody wants one, I hope you'll just send me an email and request that. Data is the food of machine learning, and if you don't have enough food, you starve. So, we do have a few tricks in this particular notebook where to explore the data, and I'll just scroll down because here we're preparing our data set. And now we're examining the data. We can actually change some of the predictive parameters. You'll see that in a moment. So here we're taking a couple of time intervals. As I said, we're taking related data sets here. Let me get rid of a little bit of stuff up there. There we go. I could probably get rid of this too. There we go. Make this a little bit easier to see. So on the left, we have kilowatts consumption for different periods of time, different times of days. These are all different data sets that are going to be correlated to do predictive analysis based on perhaps these exact conditions in the future. So next up, we split the train and test data sets. We can see that we have set a frequency here of 2 hours. We've calculated a prediction length for 7 days, and a context length is identical. We begin our training data set at this particular day, which we know from looking at the data. And as we move down just a little bit here, we're doing more of the same of getting that data prepared and set into our S3 bucket. Now we're ready to train the model. So once again, we're going to use our estimator wrapper as we've done here. We're going to use a C4 extra large. We just give the job a name. And here are the hyperparameters that we're going to use. We're going to do 400 epochs, early stopping at 40, mini batch 64, learning rate with 5 zeros. And then we have our context length and prediction, which were set above, which we simply translate. All right, there we go. So then we train the job. And I'm going to scroll to the bottom here just to see how long this particular one took and help everyone out there. Notice the wall time here was 11 seconds. Billable seconds was 563. The delta there is usually the amount of time it takes to copy the image out of S3, to just get your place in the queue and grab that image. So there's a little delta there, but typically when jobs take, let's just say more than 5 minutes to run, that startup time is not significant. Now we're going to create our endpoints. Once again, we're using a convenience function to help us prepare our data to actually test with. And now we're going to make some predictions. So we're setting up our predictor here, and we're taking a look at some of that data from our very first prediction. And if I have this correct, here we go. So here is where we've built into this notebook, excuse me, the ability to take our predictions and modify them a little bit. And this is a really nice built-in feature. So all you have to do is start with the default values and click Run Interact. Now that's going to generate a model for us. And we can see, as we did on the other notebook, that we generally do pretty well. Now this is on real data, so that makes it a little bit more interesting. If we change some of these parameters a little bit, let's lower our confidence level, and this time maybe I'll show samples, and we run interact again. We can generate more data on the fly. That is a really nice tool. I'm going to turn off that show samples just so it's a little bit more clear. It looked a little too ghosty that way. So this is a nice little tool to test your predictions. And yeah, it's just built right into these notebooks here. So I encourage you to use that. We do a second test here, which uses the dynamic feature field. And here we have our data. The feature here is, of course, something like a peak period. Maybe when you're looking at electricity demand, it would be something like a lot of air conditioning is required on that day, or some industrial park is reserved a lot of data, or you can also have an outage. And you can see here that we have some missing data, right? So there is missing data. I'm going to just go right to the predictive part again at the end. We're building a new model, and I want to see how long this one took to train. Let's just scroll down here. Good. This one took 24 minutes. So plan your lunch accordingly. But this is a worthwhile build. Once again, we see some of our top level data. And then once again, we also get the ability to play with these predictions a little bit. Notice that because data was missing in our sample, in our training data, that it's missing in the charts as well. So that's good stuff. That is DeepAR. It's a beautiful thing. I have a number of links that are available to everybody that I think are very helpful. I don't have anything here on the stock market. I gave you all my stock market information just in the beginning. But this book right here, Forecasting Principles in Practice, that's a free online book. Highly recommend it for anyone interested in this as a field. And then also all of the other materials that in one way or another supported creating this presentation. Finally, I have links not only to all of the notebooks that were used in this presentation, but also to this great series by one of our engineers in-house, Sunil Malia. I'll just bring it up. It's a great resource. It's up on GitHub. You can download it. And the way he's done this is he walks through pretty much everything you need to do univariate, multivariate, and time series forecasting. It's a really nice tutorial series. So I encourage everyone to take a look at that as well. Now, I went a little bit past the presentation time. I wanted 15 minutes. We only have 10, but I'm happy to take a few questions.
Hi, Chris. This is Chris Burns. I've been answering a couple questions here in the background, more on logistics rather than the specifics about the DeepAR algorithm. So if anybody has any questions now, as Chris mentioned, it'd be a perfect time to either write them in the box here or put them in the chat window.
So I'll just mention while we're waiting for our questions to come in. And Chris, just so you know, I can't for some reason read the questions, so I'll need you to read them to me.
Yeah, we did have one that just popped up, Chris.
Okay.
And the question is, could you go into a little more detail?
Yeah.
Sorry, I was put on mute there. It says, could you go into a little more detail how DeepAR treats categorical variables? Is it generating a separate model for each value of a category?
That is, well, because of, well, first of all, I'd refer you to the documentation. We did see an example of the outcomes in both the toy and the electrical model for handling that. It's really a byproduct of the way that we're using LSTM and the sequence to sequence. So I'll just point out that sequence to sequence is an encoder decoder model that has its roots in language processing. So, you know, the way you take a French expression, translate it to English, and use it as an encoder decoder, creates some characteristics that, when applied to this particular problem, that create windows for the RNN to operate on. Now, I will just tell you straight up, I don't know if it's creating a separate model, but because of the virtues of those particular algorithms, that wouldn't be my guess. So rather than say something, put my foot in my mouth, I'll say, please refer to the documentation. And I hope that gave you at least a little running start.
All right, great. Thanks, Chris. And we do have another question here. When the algorithm makes a prediction using the dynamic features, you are required to provide a value for each dynamic feature across the prediction period. And so then the question is the typical approach to train a DeepAR model on each of the dynamic features?
Well, that's an easy one. No, because that is what we're doing for you in the background. Once again, for details, refer you to the documentation. It's very well documented in the PDF that we have on the SageMaker documentation page.
All right, just another one just popped up. Perfect timing. Can you use DeepAR to do failure forecasting without knowing when a failure happened?
So the short answer to that would be within the probability range, yes. You know, failure is a special condition, and we saw how those special conditions were handled in the second notebook. But, you know, if you've got an 80% range of probability, you have a 20% range of improbability. So, you know, I would say with your specific instance that, you know, if you know the data well enough, you have to qualify this thing 100 times, then you should be able to at least, you know, put your team on alert, say, if you know that an adage is well predicted.
All right, thanks, Chris.
Oh, and I'll just add one more bit of color to that too. One way I've seen a lot of these models chained together is in supply chains, right? So if you have, 50 parts that you need to create a particular OEM'd product, and you either control or have access to the production characteristics of those of that supply chain. This is an instance where you can really do some rewarding, well, not failure necessarily, but outage analysis, and get ahead of being out of a product that you want to sell.
All right, Chris, we have a participant that's going to ask the question verbally here. It's a little bit difficult to
yeah, go ahead.
To touch. I'm going to take him off of mute.
Yep.
And we should be live.
So, yeah, this is Ryan Gross. I think we've met before. I was asking the question on dynamic features before, and I just wanted to clarify. So, when we're specifying the actual prediction request, it seems to fail if we don't actually provide some value for each of the dynamic variables into the future in the time period that we're trying to predict. Is that your understanding of the way it would work?
So are you, well, we accept NaN values. Are you leaving them empty, or are you putting
maybe
in
so?
NaN?
Yeah, the array length is the issue. If we just put in not a number, it will.
Yeah, just put NaN in.
Use that feature that you were talking about earlier.
Yep.
That is great to know. All right.
I mean, that's maybe a side effect of the encoder.
Yep.
Sequence to sequence encoder.
That it just requires the exact sequence. Yeah, the right sequence length.
Yeah.
Okay. That should help. Thank you.
All right. Well, if we're running down on questions here, that's fine. It's we're pretty much in. I'm grateful for the opportunity to share this information with you. Contact information is here. Chris and I, we're the PSAs here to support you. So please reach out, and as you begin to play with this and experiment, you're going to hit blockers, and give us a call when that happy day comes. So thank you very much.
All right, thanks, Chris. And Sue, I'm going to jump in and just reiterate there what Chris said. If you put a question here, we didn't quite get to that, know that you were part of the ML competency, and Chris and I are here to enable you across the entire AWS ML stack. So in the event that you didn't get a question answered today, or a question pops into your mind an hour from now, reach out to us by email, or if you want to call us, I'll give you Chris's phone number. You can call him directly. Otherwise, we're here by email 24/7.
Awesome. Thanks, everybody. Chris, that was fantastic. And Chris Burns, thanks for helping us get through those questions. I've got one more question to ask everybody. It's a philosophical question. If a webinar happened and there wasn't a survey at the end, did it really even happen? I mean, this is a philosophical experiment we are clearly trying to answer here at AWS. So you could help us out. We're going to send you a follow-up email. It's going to have a link to a super short survey, 4 questions. It's going to have a link to the replay of today's call. So if you want to dig back through, you can do that. And it's also going to have the link to our next webinar, which is going to be 2 weeks from today. It's going to cover blazing text. So with that, we will end the call, and I wish everybody a fantastic rest of your day.